Hi, my name is Adela De Pavia, and today I'm going to talk to you about a recent paper on fast algorithms for hypergraph PageRank with applications to semi-supervised learning, which I worked on along with my co-authors, Konstantinos Amaranis, Lorenzo Recchia, and Erasmo Tani. So given a set of nodes V, a hypergraph is a collection of nodes and hyperedges, where a hyperedge is an arbitrary subset of nodes. So here we represent nodes in blue, and then in black, we've drawn circles around subsets of nodes indicating hyperedges. So this diagram shows a hypergraph with two hyperedges in it. We care about hypergraphs because they are good models for the kinds of group relationships that commonly show up in real-world data. So imagine that we were trying to model some data set of emails. The way that we would do that would be to create a node for every person represented in the email data set, and then to create hyperedges by creating one hyperedge for each email and adding to that hyperedge the nodes of every person on that email. So here, this is a diagram of the hypergraph that we would produce if we tried to model emails 1 and 2. What kinds of learning problems can we solve using hypergraphs? So let's consider a simple setup where we're given a data set of emails from a company. This email data set contains both company employees and outsiders. Say we're also given some small set of labels. So for a subset of people, we know whether or not they are company employees. And our goal is to estimate for every person in the data set whether or not they are company employees using these provided labels and the structure of the email data set as encoded by a hypergraph. So to restate this problem, we've been given a label vector y, which represents whether or not somebody is known to be a company employee. And we want to find a vector that is similar to y, but very smoothly over the hyperedges. And the reason for this is because we have a belief that company employees are more likely to be on emails with other company employees. So how do we turn this into a mathematical problem? One common approach in learning literature is to create a regularized optimization problem, which seeks to minimize a combination of two terms. The first term, 1/2 norm of x minus y squared, promotes solutions that are similar to the given information y. And the second term, 1/λ r of x, is a regularizing term, which promotes specific forms of structure in the solution x. Here, lambda is a regularization coefficient that manages the trade-off. So to use this framework for learning with hypergraphs, we would first need a set of regularizers that penalize variation over hyperedges, and then fast algorithms that can solve the resulting problem in equation 1. So these two issues are the core focus of our paper. We formulate an expressive class of hypergraph regularizers and develop fast algorithms for solving the resultant learning problems. In particular, we also prove formal convergence guarantees about these algorithms. In addition, we conduct empirical studies looking at both the speed up that our algorithm offers over existing methods and showing that using hypergraph models can improve classification accuracy compared to other existing models. So to give a brief overview of the results in the paper, we study a very general class of hypergraph potentials, which are produced by considering a weighted sum of hyperedge potentials. Each hyperedge potential is a way of measuring variation over the entries of that hyperedge. So in particular, we study the setting where all the hyperedge potentials are convex, two positively homogeneous, and satisfy a normalization assumption. So one key example to keep in mind is a setting where each hyperedge potential is some scaled squared norm. So given these hypergraph regularizers, we can form an optimization problem as shown in equation 2. And then we develop fast algorithms for solving this optimization problem. So in particular, we give an algorithm that computes a multiplicative epsilon approximation to the value opt in a number of iterations that scales like 1/epsilon squared times 1 plus lambda over lambda g plus lambda, where lambda, you'll recall, is our regularization coefficient, and lambda g is a spectral gap of our hypergraph. So notably, each iteration of this algorithm requires time linear in the size of the hypergraph, in contrast with some existing methods which require super quadratic time in the size of the hypergraph for each iteration. In summary, we study a large and expressive class of hypergraph regularizers and develop fast algorithms for solving the resultant learning problems. As I said before, we also conduct empirical experiments looking at both speed up and classification accuracy. And I highly encourage you to check out our manuscript or poster to look at those empirical results. And if you're attending ICML in person, we would love to talk to you, and our poster information can be found on this slide. Thank you very much.